All right, here we go. So in this video, we're going to learn about what is called a system of objects. All right. So before we do anything, I guess we should define the word system. All right. So a system is just a collection of objects. All right. And for us, our system is going to be a collection of one or more objects that move, or maybe they don't move, but whatever they're doing, they're going to do it together. Okay. So the first example we're going to do, we're going to have two boxes sitting on a table like this, and we're going to have somebody, I don't know, maybe it's Roy, come along and push the objects, all right? And you can see that obviously if box A moves, it's got to push box B, and as a result, box B will move, and they'll both move together. Or maybe there's enough friction that the boxes don't move, right? But they're both going to kind of do the same thing, right? Now, for this problem, then, there are basically three different systems we can consider. We can consider the system of just box A, we can consider the system of just box B, or we can consider the system of boxes A and B, all right? And these are all valid systems that we can consider. And we can make a free body diagram and will make a free body diagram for each of these three systems. Okay, we'll make a free body diagram for object A, free body diagram for B, and a free body diagram for the two object system. Now, when we do this, it is important that the only forces that we put on our drawing are what are called external forces. All right, in order to be an external force, it has to be a force that's exerted on an object in the system by an object which is outside of the system. Okay, so if I consider box A, so that's my system, then gravity would be an external force because gravity comes from the Earth and the Earth isn't part of my system. All right, if it's sliding across the ground, there's friction. Again, that would be an external force because it comes from the ground, which isn't part of my system, right? As it moves, it's going to push box B, and box B will push it. That's an external force. So there's the two boxes push each other, right? Because they're touching each other. But the force of box B here would be an external force because box B isn't in the system, all right? Now, if, on the other hand, I consider the system of both boxes, if I consider this system, now that force of box B pushing box A and the force of box A pushing box B, those are now what we call internal forces, and so they will not go on that free body diagram, okay? So you only put a force on a free body diagram if it is an external force for the system that you're considering, okay? And remember, depending on your system, a force can be either internal or external, okay? If I consider just box A, then the force of B is external. Whereas if I consider both boxes, now that force is internal, okay? So, here we go. Now, problem-solving strategies for these systems. So my suggestion is you follow this kind of sequence for solving the problems, right? So the first thing we're going to do is we're going to consider the system that has multiple objects in it, and we're going to kind of just think about what's this system going to do? Is it going to move? If it does move, which way will it move? And what you're going to do is you're going to choose the direction of acceleration and make that positive, all right? Now, in the first example we do, that's going to kind of be a non-issue. But in the second example, this step here will be much more important, okay? All right, once you've done that, you're just kind of thinking about the multiple object system. Once you've done that, what you're going to do is you're going to make a free body diagram for one of the two objects, say object A. You're going to go through and you're going to label all of the forces. But what's going to happen is 9 times out of 10, you're going to be missing at least one force. That's okay. Just label it, like make a note. Oh, I don't know the force of blah, 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 blah. Label it and move on. All right? Then you're going to repeat the exact same process for the other object. Okay? Again, you're going to be missing some forces. So once you've kind of done as much as you can on the free body diagram of the individual objects, now we go back and we make a complete free body diagram for the multiple object system. So what's going to happen is now we know all of the forces and we can use that to find the acceleration. Now remember, both of our boxes are moving together. So if we know the acceleration of the system, the two object system, then we know the acceleration of the individual boxes. So now I can go back to object A, I know its acceleration, and now I can find the missing forces and then repeat the same process with object B. All right, a lot of words. This will make a lot more sense when we do an example. So I'm going to do that now. Here we go. All right. Oh, before we do, a quick comment, which I already alluded to. Please don't forget Newton's third law, right? In that last example, we had box A and box B, they are going to push each other, right? There's going to be the force of A pushing B forwards and the force of B pushing A backwards. That's an action-reaction pair. Every one of these systems is going to have an action-reaction pair like this, all right? And please remember that our action and reaction are equal and opposite, okay? That's going to come up again and again and again this section, all right? Okay, so let's do an example. So in this example, it says 2 boxes sit on a horizontal frictionless surface, as shown. Box A has a mass of 20 kilograms, and box B has a mass of 60 kilograms. Box A is being pushed to the right by a force of 240 newtons. So, like I said, let's assume that's Roy. Here's Roy, doot, 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 and he's going to push it, force of Roy, with a force of 240 newtons, okay? So step 1 on my little thing was think about the 2-object system. Well, I've got these 2 objects. Clearly, if they move, they're going to move this way. So I'm going to call positive forwards and backwards negative, all right? So in English, what this means is any force that is contributing to the acceleration is going to be positive, and anything working against it is going to be negative, all right? So that's step 1, okay? Step 2, make a free body diagram for box A. So that's what I'm going to do now. So here's box A. It's 20 kilograms. I can start with the force of gravity. It's going to be 196 newtons. I'm going to have a normal force that's also 196 newtons because it's not moving up or down. One of those 2 forces has to be negative. Notice those forces don't lie on the same axis as my acceleration is going to, right? Oops, I didn't want to do that. Those 2 forces don't lie along the acceleration axis. So I'm not really going to worry about positives and negatives. I just need to know that they're going to cancel each other out. So make one of them negative, whatever. That's negative. All right, what other forces have we got? Well, we've also got that force of Roy, 240 newtons. All right. And then we've also got, so because box A is bumping into box B is going to push box A backwards. So here's the force of B pushing A. All right. Now, I don't care how you label this. Some books will call this the force of A being pushed by B, and some books will just call it the force of B. I don't really care which of these notations you use as long as you understand that it's an action and we're going to have a corresponding reaction, right? Okay, now the other thing is I don't know what that force is. So this is what I was saying back here is that you'll be missing at least one force. Well, there we go. In this problem, we don't know what this force of B pushing A is. So I'm kind of stuck. All right, so now what I'm going to do is I'm going to move on to box B. So here's box B. 60 kilograms. So the force of gravity on B turns out to be, I guess let's make it negative, 588 newtons. There's going to be a normal force that cancels that out, 588 newtons. Those are different normal forces, so I guess I should indicate that. And then the reason box B moves is because of the force of object A pushing B. And again, notice that this and this make up an action-reaction pair, okay? And then the problem tells us that it's, the problem tells us that it's frictionless, so we don't need to worry about friction. So that's it for my free body diagrams. But notice I am, as I alluded to before, a little bit stuck, right? Because I don't know I don't know the force of A pushing B or the force of B pushing A. All right, so what I'm going to do now is I'm going to go back to my original 2-object system, okay? And let's make a new free body diagram for that. All right, so here's what I'm going to do. I'm going to do this in blue. Boop, 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 boop. Let's get rid of some of these things here. All right, so here's my 2-object system. Oops, I'm going to draw kind of a little bubble around it just so we know what we're doing here, all right? Oops. Sorry, trying to clean it up here. All right, so what forces have we got? Well, we've got these 2 gravitational forces, right? Gravity's pulling A down and gravity's pulling B down. So I'm going to go ahead and put those in their original colors. Now, sometimes it's okay to combine these, but not always. So I'm going to just go ahead and keep them separate. If you're really careful, you can sometimes combine them, but not always. And this is a problem where we could combine them. Our next example, you cannot combine your gravitational forces, and I'll show you why when we get there. All right, so we got that, and then we got these two normal forces of 196 and normal force of 588. Okay, those all cancel. And then we've got Roy pushing the system forwards. I guess if you want to be nitpicky about it, you can draw the arrow coming out over here from box A. It doesn't really matter. Just we know it's a force on the system, and it's 240 newtons. There's no friction. Now, we've also got the forces of the two boxes pushing each other, these guys that I've highlighted in yellow down below. All right? For my two-box system, those are internal, right? Because this force of A pushing B is produced by object A, which is in the system. And the force of B pushing A is produced by object B, which is in the system. So I don't need to worry about those two forces that I just highlighted with green because they're internal. So this is my complete free body diagram, all right? And what I'll notice is for this two-object system, I know my net force. So let's go over here. So for my two-object system, I know my net force is just the 240 newtons from Roy, right? Because this is the only force that doesn't cancel. So now I can find my acceleration, because acceleration is net force over mass. I've got a net force at 240 newtons, moving a total of 80 kilograms. And so that makes my acceleration 3 meters per second squared. So there we go. That's question A. That's the acceleration of the two boxes. And now that I know that, what I can do is I can come down here and find the missing forces down here, because now I know that object A is accelerating at 3 meters per second squared. And so what I'm going to do is I'm going to go, oh, I know the net force is mass times acceleration. 20 times 3 gets me 60 newtons. And now I know my net force is the force of Roy plus that force of B pushing A. 60 equals 240 plus something. Oh, that something has to be negative 180 newtons. So that's question B. How much force do the two boxes exert on each other? So it's 180 newtons, right? And then it says verify your answer. So what I can do now is I can repeat the process on box B. Again, I know my acceleration is 3 meters per second squared. Net force is mass times acceleration, 60 kilograms times 3 meters a second squared is 180 newtons. Oh, and on this object, the only force that doesn't cancel is that force of A pushing it, so that's got to be 180 newtons. And notice those two forces that are highlighted are equal and opposite because they are an action-reaction pair. All right? So there we go. That is our first example. Sorry, I just realized I'm sitting at a squeaky desk. I hope that it is not driving you nuts. I will move now. All right. Okay, so in this scenario, what we've got is two boxes. This little circle here is meant to be a pulley. So we've got box A is over here, tied to a rope, which goes and attaches to box B, and then there's some friction there, right? So what's going to happen is I'm going to have the force of gravity on object B pulling the whole system this way, and then there's some friction over here, which might be enough to keep it at rest, but if it's not, it's definitely going to accelerate this way. Now, please notice, so in this problem, what's going to happen is if it moves, object B is going to move down, and traditionally we call down negative, but object A is moving to the right, which traditionally we call positive. So this is where that first step becomes really important. Think about the multiple object system and decide on a sign convention. If possible, make the direction of acceleration positive. So anytime you've got a problem with a pulley like this one, this becomes an issue. The idea is my system can move one of two directions. Either the system goes forwards and down, or maybe if somebody pulled it this way, it could go backwards and up. For the rest of the problem, I'm going to call this way positive and this way negative. So any force that contributes to motion forwards and down is going to be positive. Anything working against that will be negative. Okay? So now what I'm going to do is consider the individual objects, okay? Oh, shoot, I guess it doesn't really, well, yeah, let's do this. I want that to be blue. Okay. Okay, so let's make a free body diagram for box A. So here we go. So here's box A. The problem tells us the mass, so I can go ahead and find my force of gravity. And there's a normal force canceling that out. Again, one of these has to be negative. It doesn't really matter which one. Now, there's tension on this, right? So here's my tension. Now, remember, that tension is caused indirectly by object B, right? That tension just allows B to pull A forwards, all right? And then we're going to have some friction over here. I don't know yet if it's going to move or not. So let's take a second and find our maximum static friction and our kinetic friction. All right, and the problem gave me the two coefficients of friction. So I'm just going to do coefficient times my normal force to get those forces. This turns out to be 14.7 newtons. No, it doesn't. 1.47 newtons, my apologies. And the kinetic friction is 0.882 newtons. Okay, but I'm kind of stuck there, right? I don't know the tension. I don't know if it's going to move or not, so I don't know whether it's kinetic or static friction. So now I'm going to move on to object B. All right, so here's my object B. I know that the mass of object B is 0.2 kilograms, so I can go ahead and put in my force of gravity. It's going to be negative 1.96 newtons. And then we've got tension holding it up. Now, this is super important. This tension only equals this, the force of gravity, if the object isn't moving. And remember, both of our tension forces are equal. Students year after year after year make this tension over here equal to this force of gravity. And you cannot do that, because if the tension equals that force of gravity, then object B won't move, and as a result, object A can't possibly move, all right? So that tension is an unknown force, okay? If it helps any, this is analogous to the force of A pulling B, and this is the force of B pulling A. Those are an action-reaction pair. So let's go ahead and highlight those. That's my action-reaction pair. Action, reaction, or vice versa. All right, but I'm stuck. All right, so now what I'm gonna do is I'm gonna go back up to my two-object system, and I'm gonna make, I'm gonna make a new free body diagram, all right? So what are my external forces? Well, force of gravity on B is external, so that's negative 1.96 newtons. But now the tension is internal, because that tension is just allowing the boxes to pull one another. All right, and then over here I'm gonna have gravity and normal force. So those are the same numbers as below, and I'm gonna have friction. Okay, now we can decide if it's static or kinetic, right? Because if the object is going to move, sorry, let me say that again. In order for static friction to prevent the object from moving, I've got 1.96 newtons pulling it forwards. My static friction would also have to be 1.96. But I've only got 1.47 newtons of static friction, which is not enough. So we got to switch over to kinetic friction. So I'm going to go ahead and put that on my drawing now. Okay, so here we go. This is kinetic friction, 0.882 newtons, negative. And over here, kinetic friction is negative 0.882 newtons. Okay. Sorry, I got a little cluttered here. All right, so now what I'm going to do is, for this two-object system, those are all my forces, because the only other force is tension, which is internal, so I can find my net force. So that's going to be, oh no, oh, I made a huge mistake here. I'm so mad at myself. Remember at the beginning, I said this way was positive? That means over here, this way is positive. This force of gravity is positive 1.96. I made it negative out of habit. It's positive now because it's contributing to the acceleration. That means this is also positive. Okay, the direction of acceleration is positive. All right, so now I can find my net force by doing that 1.96 newtons plus negative 0.882 newtons from friction, right? This is negative because it's working against that, it's working against my acceleration. All right, so this gives us a net force of 1.076 newtons. And now I can find my acceleration, because acceleration is net force over mass. My net force is 1.076. My mass is the full 0.8 kilograms. So this gives about 1.35 meters per second squared. So there's my acceleration for the system. Okay. And so now that I know what my acceleration is, now I can go back to these other free body diagrams. So for this guy, net force, mass times acceleration. So the mass was 0.6, the acceleration's 1.35. Multiply that out and you get 0.81 newtons. And so now I can go net force is tension plus kinetic friction. 0.81 equals tension minus 0.882. And so the tension turns out to be 1.69 newtons. And now I can come over here and check my answer. My net force is mass times acceleration. And that gives you 0.27 newtons. Net force is 0.27. Oh, sorry. I'm trying to hurry here to beat the bells about to ring. So I got gravity and tension. So 0.27 equals positive 1.96 plus tension. Subtract the 196 from both sides and your tension turns out to be negative 1.69 newtons. And I am happy because they are equal and opposite. All right. So that is how to solve systems of objects problems, okay? These are long problems. They're kind of a drag, but on the bright side, once you figure out how to do them, the process is always the same. All right, so there we go.